Good morning, students. Today I want to demonstrate to you the first experiment, which is the DC power supply. This particular experiment has three parts. So the first part we will look at half-wave rectifier and full-wave rectifiers. The second part we would use a capacitor as a filter so that you will know about unregulated DC power supplies. Third part, we will have regulated DC power supply using a Zener diode and also using a standard voltage regulator IC. So let's come to the first part. What I have here is the half-wave rectifier circuit, which uses a standard IN 4001 power diode, which has a capacity of about 1 amp and has a peak inverse voltage of 1000 volts, and I have a load resistance of 22 kilo ohms. What I have done is I have a center tap transformer. So I have these three wires here. The black wire is the center tap. This red wire and this green wire, they are the 15 volt RMS point. So we would use this transformer for our experiments. So what I have done is I have connected the center tap to the ground, and I have connected the red wire, which is the 15 volt wire, as the input to the half-wave rectifier, and the load is 22 kilo ohms. Let's have a look at the waveforms. Let's have a look at the waveforms. So what we have here is the input sine wave, and you have on the bottom waveform, which is channel 2, you have the output of the half-wave rectifier. So the measurements are shown here. Channel 1, you can see the frequency is about 50 Hertz, and channel 1 peak to peak is showing us about 48 volt. Channel 2 frequency, and channel 2 peak to peak is showing roughly about 23 volt, which is nice because you have a voltage drop of about 0.6 to 0.7 volt, and that's nicely matching. Now what I want to show you is, now let me merge these two waveforms, and so that we can have a much better, we'll try to overlap these two waveforms. What I will do is, let me bring this to the origin and let me align the other one also, then we can have a much better, so now I aligned it. So you can see that, you can see it very well, the half-wave rectifier circuit working very well, and you can also see there is a small gap at the top which corresponds to the voltage drop. Now let me expand this particular waveform, and you see that you don't see a clean sine wave. If I expand it further, it's even more evident. You can see that there is almost a flat top in the sine wave. This is because our input which we get from the transformer from our power supply, unfortunately the power quality is very poor. One of the major reasons is because today we all use power supplies, switching mode power supplies, and especially in laptop or computer. So because of all this, there is a heavy inductive load, and this gives you this kind of a waveform. So we will see this later. We will compare this with a function generator, and we will see how the function generator sine wave and this particular sine wave compares. Now let's look at the full wave rectifier circuit. Now let's come to the full wave rectifier circuit. For the full wave rectifier circuit, we have two circuits. The first one would use a center tap transformer, the one we have. So what I have done is, I have used the center tap, which is the black wire, as the ground, and the red wire, which is the one of the outputs of the center tap transformer, goes to one of the inputs, the anodes of the circuit, which is the first diode. The second center tap output I have connected to the second diode. So this is what you do. Using two diodes you get a full wave rectifier, and once again, like the last case, the load resistance is a 22 kilo ohms resistance. Let's see what we get at the output. Let's see what we get as the output of this full wave rectifier circuit. What we have here on the top is the input, one of the inputs. Now what we have at the bottom on channel 2 is the output. Okay, look at channel 1, the input waveform, the frequency is 50 Hertz and the peak to peak is about 50 volt. And look at channel 2. The channel 2 frequency is 100 Hertz, very important, 100 Hertz, because it's a full wave rectified waveform, very important. And the channel 2 peak to peak is roughly half of this. Now what I want to do, like last time, I want to once again superimpose both the waveforms. So let me do that. I would just superimpose these two waveforms so that you can see them better. So I would both of them, let me superimpose. So you can see that, just like last time, you can see the waveforms. So only one of the inputs is shown. So you can see that these two are matching, and during this particular waveform which you see in the negative half here, corresponding to that you get the output, rectified output. So this nicely shows. Once again, just like the previous case, you can see there is the waveforms are distorted, which we said is because of the power which we get, the AC power we get is unfortunately the quality is poor, primarily because of the very heavy inductive load and the switching mode power supplies we use all over the world now. Especially in all our appliances we use switching mode power supplies. So now we have the third circuit, which is the bridge rectifier circuit, which uses 4 diodes. So let me show you the connections from the transformer side. So we have the center tap transformer, and very important to note that I have not used the second output of the center tap transformer. I have used the center tap, and that I connected to the one of the inputs, AC inputs, and the center tap I connected, and the one of the center tap the transformer outputs I connected to the other AC input. Now the positive output is our output, and the negative I have connected as the reference here. Now I will show you the outputs of this particular waveform. Now let me show you the output of this particular bridge rectifier. Now one problem we have here is I am showing you the output of the bridge rectifier only. You may be wondering why I am not showing you the input. Now we have a problem, because the bridge rectifier, you would have seen that both the circuits which we used earlier, both the half wave rectifier and the full wave rectifier circuit using 2 diodes, you would have seen that in both those cases the center tap was the ground. In this particular case, the center tap is not ground. In fact, if we use the center tap because we want to get input as 15 volt. If I use the green output which we had there, you would have got double, you would have got 30 volt as input. So we don't want to do that. So here we cannot show you the input because the oscilloscope, one of the inputs is ground, and you can't short the input. If you do that, it will not work. So I am able to show you only the output waveform. So this is something to remember when you do the bridge rectifier. You should not connect the oscilloscope to the input. If you connect one of the diodes, you will get shorted and you will not get the full wave rectifier output. Yeah, here once again you can see, let me show you the waveforms here. You can see once again so right now I am using only channel 1 because as I told you I cannot show you the input waveform. The channel 1 frequency you can see once again is 100 Hertz. So proving that it's a full wave rectifier, whereas the input frequency was 50 Hertz. And the peak to peak waveform the amplitude is roughly half, okay, of the about 25 volt which we got. So that way now we have come to the end of part 1. We are seeing half wave rectifier and we are seeing 2 full wave rectifier circuits, one using 2 diodes and one using a bridge rectifier. Yeah, we will now see the part B. So we are coming to the part B of the experiment. What I have done is I have taken the half wave rectifier circuit. This time, this part B of the experiment, we are concerned about unregulated DC power supply, which means we have a capacitor. We will use a capacitor to smoothen the output waveform. So what I have done is I have connected, so we have a load of 22 kilo ohms and I have connected here a capacitor of 470 microfarad. I'm sorry, we are using a capacitor of 1000 microfarad. 1000 microfarad. Now what is most important to notice here is when you have a electrolytic capacitor, you need to follow the polarity correctly. So I have connected the negative polarity to the ground and the positive to the output, and I have a 22 kilo ohms as load. What I will do is I will use 3 resistor values, and one is 22 kilo ohms as a load resistance. I will use a 10 kilo ohm as a load resistance, and then I will use a 1 kilo ohm as the load resistance. For all these 3 cases, we will look at the ripple voltage we are going to get, and that would give us some insight about how good or bad is this particular unregulated power supply. So we will look at these 3 waveform corresponding to these 3 resistors. We will look at the output waveform and the ripple. So what we are seeing on the DSO are 2 waveforms. One is the input waveform, which is the sine wave, and what you are seeing is that straight line which you are seeing is the unregulated output waveform. Now you are not able to see any ripple because that ripple is very, very small. Let's try to measure the ripple correctly. So to do that, what I am going to do, I am going to put the channel 2 into DC coupling, which means it will only show the I will put in the AC coupling. So I would show you, so it will show you only the AC value. So now what I will do, I will increase the sensitivity of channel 2. Now you are able to see ripple coming. So the peak to peak ripple, let's measure in channel 2. So the peak to peak ripple you are getting is somewhere between about maybe about the lowest I got was 48 to almost about 60, 70. So the important thing to notice here is, let's try to now align this waveform and understand. Okay, yeah, so you can see that when, so this particular period of this rising period corresponds to the half cycle when the diode is conducting, and this discharge waveform you see here corresponds to the time interval when the diode is not conducting. So the capacitor is discharging. Now the ripple here is quite small because the load resistance is quite high, or the current. So roughly the amount of current right now, because we know that the output voltage is about 25 volt. I have a 22K resistance, load resistance. So the current is roughly, let's say, about slightly more than 1 milliamp. That's why the ripple is very small. Now I want to change this resistance to 10 kilo ohms. So let me change this resistance to 10 kilo ohms and let's see what would happen to the ripple. So now it's the 10 kilo ohm, and you can see that the ripple has substantially increased, and the ripple voltage is now almost doubled. It's about 100, somewhere between 100 to 120. Okay, so you can see the shape of the waveform has changed. You can see that discharge cycle, you can see it very well, is discharging during the discharge cycle. As you know, the capacitor has to supply the charge, and that is very nicely visible. Now one question which arises is why there is a large gap here. In the textbooks, these two should be they should be together. One of the main reason is, there is when we draw in the textbooks, the diode drop is ignored, but a major reason is this is a power diode and it has a lot of capacitance. So therefore some of this is because of the switching delay of the diode. So that is very nicely seen. So we see here that the ripple is almost doubled. The peak to peak ripple is almost doubled. Now let me put the last value, which I want to put a 1 kilo as the load, and let's see what would happen to the ripple voltage. So I put now 1 kilo as a load, and you can see that the ripple is very high, and ripple voltage is in the order of 400 plus. Okay, so 430, and you are just looking at it, you are able to see that the ripple is very high. So let's say almost half a volt of ripple. But once again, if I go back to the DC mode, so you would see that this ripple is very small. So what we have learned from this particular experiment is the ripple is a function of, for a given value of capacitor, the ripple voltage is a function of the load resistance or the load current. If the load current is large, then the ripple will be more. If the load current is small, then the ripple will be small. Now for a given load resistor or load current, if I change the capacitor value, you will increase the capacitor, you will see that the ripple will decrease. So this is we will not do that. So this is just to explain. Now let me go back to the coupling, let me go back to DC for this case, and you would see that you are not able to see the ripple. It looks like it looks very much like a straight line. So this is something important to notice, that with an ordinary naked eye, just looking at the DC output, you are not able to see, because the output voltage is of the order of about 20 volt, and so the output we are getting here is for this particular case, the output is about 20 volt, and the ripple we have is about half a volt. That's why we did not see. Let's now consider the full wave rectifier cases. So what I have done here is I have taken the second circuit, which is the center tap transformer and two diodes, the full wave rectifier circuit, and once again the same 1000 microfarad capacitor is put here. Once again, very important to connect observe the polarity for the automatic capacitor, otherwise it will explode. So the negative terminal is connected to the ground, and the positive terminal is connected parallel to the load resistance. I have used a 22 kilo ohm resistance, just like the half wave rectifier circuit. So what I want to show you, the output waveforms. So you can see on the DSO two waveforms. One is the input waveform, and this is the center tap transformer. Therefore, one of the inputs is ground, so I can show you the input waveform. And the output you are seeing on the channel 2, which is a straight line. So the channel 1 and channel 2 are 10 volt is the vertical resolution. So you can see that it's corresponding to the peak. Okay, so it looks as though there is no ripple, and the load resistance is 22 kilo ohms. To see the ripple, what you need to do is, because the ripple is very small, you need to go to the AC coupling. So what I'll do, I'll first go from DC coupling to AC coupling. Now you see that I need to, since it is going to be very small, I need to increase the resolution. So now you are able to see the waveform. So let's measure the peak to peak ripple. Yeah, now you are able to see the ripple, and the peak to peak ripple is somewhere between about, I think around about almost about 50-55 millivolt. But what is important to notice here is that, let me just superimpose these two. You are able to see there is a delay, which I said is mainly because of the switching delay of the diodes. But this the discharge period is very visible here, and the charging period of the capacitor is also seen. So what is important to notice here is the ripple is quite small. Now let me change the load resistance. Let me use a 10 kilo ohm as the load. Now you are able to see that the ripple has increased, almost doubled, it has almost become doubled, and there is a lot of noise here, and also there is a difference between the positive peak and the negative peak, and one of the reason could be because of the unequal voltages of these outputs. Also this can happen, but most important notice here is the ripple is almost doubled as expected. So now let me change that resistance once again, and let me use a 1 kilo ohm resistor. Now you are able to see that the ripple is now very high, about 300 millivolt. Now if you remember, when we had a half-wave rectifier for the same value of 1 kilo ohm, the ripple was more than 400 millivolt, and here you see that the ripple is of the order of 300 millivolt. So this is something very important. So one of the important observations is that a full wave rectifier will give you much less ripple compared to a half wave rectifier, which you are able to see. But unfortunately, when the load current is very small, this difference you will not be able to appreciate. But when the load currents are high, like this particular case, you are able to clearly see the difference in the ripple between a half wave rectifier circuit and a full wave rectifier circuit using just one capacitor. What I am showing you here is the output of the function generator which you will be using, the AFG which you will be using. Now you can see on the DSO, the waveform is quite clean and it looks like a proper sine wave. Now in order to see this better, to see whether it's a pure sine or not, we can do the FFT, or the fast Fourier transform. Now the DSO which you are using in the lab has this capability. So let me take the FFT of this waveform, which will show you the Fourier components, Fourier series components. So so you can see the FFT. What I will do is now I would adjust so that the x-axis is 50 Hertz per division, so that we can see it well. And what I have done is that so what I have seen, this first one, this is the zero frequency, and this peak you are seeing is 50 Hertz, because we have chosen 50 Hertz as the frequency on the function generator. Now what is most important to see here is you can, the peak which I am seeing here is, let me align it, and the vertical scale is 10 dB. So right now the floor is about 1, 2, 3, 4, 5. It's less than 50 dB, and the dB you would know, and since we are applying voltage here, 20 log V2 by V1. So this noise, so you can see the harmonics are all negligible because it's close to 60 dB less than the peak. So this is negligibly small. We would compare this with the transformer which we are using to see the quality of the 50 Hertz waveform we get from there. This is just to illustrate. So let me just now go to the transformer which we were using. So I will connect the transformer. So this is the center tap of the transformer. Let me connect that to the ground wire here, and one of the outputs here, let me connect to the channel 1, and let's then look at the results what you're getting. So let's give it a little bit time for the waveform to settle down. Effectively takes some time. Now this is very shocking. You're able to see here once again the same thing, 50 Hertz. So let me just lower it. Let me position it. Okay. So what you are able to see is that the peak, 50 Hertz peak is here, but you can see here the third harmonic, second harmonic is also there, which is low, but look at the third harmonic. The third harmonic is 10, 20, 30 dB down. So you have a huge third harmonic component, and second harmonic is also there, this 100 Hertz. Third harmonic is very dominant, and you have fourth, nothing is there, but you have a fifth harmonic. So these harmonics are the ones which are giving you that kind of, so you are able to see that the sine wave which you are getting from the transformer is not a pure sine, and you would see that in comparison to that sine wave, the one which you are generating using the arbitrary waveform generator in the lab is quite clean. This is just to explain to you the real life sine wave which you get from the transformer, how poor in terms of its sine wave, the power quality or the waveform purity is so bad. This is just to explain to you.